All right, here we go. This is problem number 83 from chapter 9 of the Halliday and Resnick textbook. We've got these two blocks. I know that the mass of, whoa, I know that the mass of the block on the left is 1 kilogram, and I know that the mass of the block on the right is 0.5 kilograms. That's a terrible 5, but that's a 5. All right, and the idea is they're held together with a spring. And they're held in place at rest. So the idea is, through this whole problem, the velocity of my center of mass has to be 0. All right? So there's two ways of solving this. And to be honest, probably the easiest way to solve it would be using conservation of momentum. But since we haven't learned about conservation of momentum, at the time that I've assigned this assignment, I'm going to do it in terms of the center of mass. Okay? So here's what I know. I know that the velocity of center of mass must be 0 because the spring is an internal force, right? It's basically a means of block L pushing block R and block R pushing block L. So since the net force on the system is 0, that means the velocity has to stay constant. Since the initial velocity is 0, the velocity's got to stay 0, right? So here's the deal. So in part A, it says the spring gives block L a release speed of 1.2 meters a second relative to the floor. So all of these, when I talk about the velocity of center of mass, I'm talking relative to the floor. So how far does the block travel in the next 0.2 seconds? So here we go. So the velocity of the center of mass should be the mass of block L times the velocity of block L relative to the ground, plus the mass of block R times the velocity of block R relative to the ground, divided by my total mass. Mass on the left plus the mass on the right. So we get 0 equals 1 kilogram times 1.20 meters a second. But notice it's going to go this way, which means I got to make that guy negative. Plus the mass of the block on the right is 0.5 kilograms times the velocity of the block on the right all over 1.5, right? So let's multiply both sides by 1.5. That goes away. And solvify this, right? We're going to get what? This is 1 times negative 1.2. Add it, so you get 1.2 equals 0.5 times the velocity of the block on the right. So you get 2.4 meters a second equals the velocity of the block on the right. So that means that the displacement should be velocity times time, right? So 2.4 meters a second is how fast that block is moving. It's going to do that for a time of 0.8 seconds. And so you get whatever that answer was, right? 1.92 meters, it looks like. All right, so that's the deal there. All right, so doing it using conservation of momentum, I guess really it's the same thing, right? Because your total momentum before the collision has got to be 0, right? Before the collision, sorry, before they push each other, your total momentum is 0. That's got to equal your total momentum after the explosion. So our total momentum before is 0. Our total momentum after is, oh, well, that's this expression. So I guess it ends up being the exact same thing, right? Okay, so let's do part B. Let me clear up the board here. Okay, now in part B, it's basically the same idea, but this time our velocities are given relative to the other block. So here's what we know. It says the spring gives block L a release speed, so the velocity, So let's see, the velocity of block L is 1.2 meters a second relative to the velocity of block R. So the idea is if block R is moving this way, then block L is going to be moving this way at a velocity of 1.2 relative to the other. So how do I want to write this? So the velocity of block L relative to R is going to, it would have to be negative 1.2, right? Meters a second. And that is the same as the velocity of block L relative to the ground plus the velocity of the ground relative to block R, which is the same as the velocity of block L relative to the ground minus the velocity of block R relative to the ground. Okay, so the idea is we know that the velocity of our center of mass relative to the ground is 0, so we want to measure all of our velocities relative to the ground. So So this becomes, let's see, the mass of block L times the velocity of block L relative to the ground, plus the mass of block R times the velocity of block R relative to the ground, over the mass of block L plus the mass of block R. So we get 0 equals the mass of block L was 1 kilogram. The velocity of block L is, I want it relative to the ground, right? Oh, I didn't finish my algebra over here. So we've got this. Negative 1.2 equals the velocity of block L relative to the ground minus the velocity of R relative to the ground. So that means the velocity of L is the velocity of R minus 1.2. So that's what's going to go here. The velocity of R minus 1.2 meters a second plus the mass of block R, which is 0.5 kilograms, times the velocity of block R. And solve that. Okay. So what are we going to get? Let's see. Scroll down a little bit, buy ourselves a little room here. So distribute the 1, you get VR minus 1.2 kilogram meters a second. Oh, notice the dividing by this doesn't matter because you can multiply it, right? And times 0, it's just going to go away. So plus 0.5 kilograms times VR. So we got 0 equals 1 VR plus 0.5, so 1.5 VR minus 1.2 kilogram meters a second. 1.5 VR equals 1.2 kilogram meters a second. Divide both sides by 1.2, and your VR turns out to be 0.8 meters a second. So your delta x then is your velocity times your time. So we'll go in at 0.8 meters a second relative to the ground times 0.8 seconds, right? So that's 0.64 meters. Okay, there we go. I think that was it, right? That's all we had to do. That's all we had to do. All right. Oops.